So let's continue now with what we were doing yesterday. We want to pick up with where we left off, and we want to continue working some examples involving u-substitution. So let's take a look at example 3, where we have the integral of 3x squared times the quantity x cubed minus 3 quantity squared. Now, when we're looking for u-substitution, we're trying to figure out what should be u. Remember that good places to find u are in the argument to trig functions, the argument to natural log, the power on an exponential, or the base of something being raised to a constant power. And then if all else fails, sometimes the denominator. All right. So let's make a list of good places to find u. So good places to find u. So that would be the base of something raised to a constant power. That's a good place. E to some power. This is a good place to find it. Natural log of some expression. That's a good example. Or a trig function where the argument is more than just x. That's also a good place to find it. Other good places would include underneath a radical. That's a good place to find u. Let's see if we left anything out. Nothing's coming to mind at the moment. So based on that, which part of the integrand 3x squared times quantity x cubed minus 3 squared do you think should be u? Anybody? What should be u?
Is it the x cubed possibly?
Yes, it's the x cubed minus 3. So we're going to take u to be equal to x cubed minus 3. Choosing u is the single most important step in solving a u-substitution problem. So you really do need to look for one of these places that you see on the right here and discover which one of them you've got. In this case, it's this one. We have an expression being raised to a number power, and that's a good indication that it should be u. The other reason it should be u is that when we take the derivative of it, and we get du dx, we get 3x squared. And we can see that 3x squared is a part of the integrand itself. So the derivative of u is a part of the integrand, which tells us that we did make the right choice for u. So now we can do an abuse of notation, and we can swing the dx around to the other side. And you have a choice at this point to either leave this as du equals 3x squared dx, since you have 3x squared dx, or if you want one method to fit all situations, solve for dx to get du divided by 3x squared. Then we substitute into our original integral. So the integral becomes 3x squared. We replace the x squared minus 3 with u. It's raised to the second power, and we replace the differential dx with du divided by 3x squared. The 3x squareds will cancel, and we'll be left with u squared du. And that will get rid of the x's. So when we're done, we should have an integral in terms of u only, and there shouldn't be any x's left. So now we have the integral only in terms of u, so we apply the power rule, looking for the antiderivative function. So this gives us u to the 2 plus 1 over 3 plus c, or we can write this as u cubed over 3 plus c. Then since we're looking for an antiderivative function, we want to go back to the original integral to see that the differential is dx. And since it's dx, we need to return to x. So we back substitute for what u is, and this gives us 1/3. I'm pulling it out front. The quantity x cubed minus 3 to the 3rd power plus a constant. And that would be our solution right there, right? That is the antiderivative function for the original function. Okay, that one didn't take too much work as far as length goes. Let's take a look at the next one. Take a few minutes to stare at this one for a moment. Think about all the good places to find u. You're looking for a function inside of a function, a composition of functions. Where do you have an inside function? Let's hear from Trevor, Jay, or Jack.
X cubed plus 5.
Excellent. Thank you, Trevor. So x cubed plus 5 is u. And then we take the derivative of both sides of that. And the derivative of x cubed plus 5 becomes 3x squared. Now, we don't have all of the derivative in the integrand, but we do have the variable portion of it, x squared. We're missing the constant 3, but we don't worry when constants are missing or when we have extra constants. Those can always be taken care of in the course of the integration. So then we abuse the notation. We swing the dx around to the other side. And then for a one method fits all, you can solve for dx to get du divided by 3x squared. Then we replace each part of the original integral. We have nothing to replace x squared, so we leave x squared as is. We replace the x cubed plus 5 with u. It's raised to the 9th power, and we replace dx with du divided by 3x squared. Now we can take the x squared that was left in the integrand and divide out the x squared that was part of the differential dx, and that will leave us with a 1/3 constant factor. So this leaves us with 1/3 u to the 9th du. Now that can be integrated because 1/3 is a constant. It can be pulled out of the integration. Then we apply the power rule. So I'm going to start skipping some steps here. So add 1 to 9, we get u to the 10th, divide by the new power, and add on the constant of integration. Again, because we don't know what the constant is. These are families of functions. Now, you've got a complex fraction here with this 1/3 divided by 10. But remember, the denominator of the numerator and the numerator of the denominator are both in the denominator. So this really gives you 3 times 10, which ends up giving you 30. And then we replace u with what it originally was, and that expression is x cubed plus 5, and it's being raised to the 10th power, and we have a plus c. So most of these should be as straightforward as that first one was. Most of them are not more complicated than that. Now, that doesn't mean that they're not complicated. They can get quite complicated and they can be quite challenging. So this is something that you want to spend time on, and you want to make sure that you understand it, because it definitely is important and it's going to be a major part of what you do from now on. Let's look at example 5. Looks like I've got a lot of extra space here. All right. Looking at example 5, I have the integral of the cosine of 2x plus 5. So again, I'm looking for a function that is inside another function. So I need an outside function and an inside function. Let's hear from Cherie, Aubrey, or Hannon. what is the inside function? What should be u?
2x plus 5.
Excellent, 2x plus 5. So u is the inside function of the cosine function. So then we take the derivative of both sides of that equation to get du, which just gives us 2. And then we abuse the notation by swinging the dx to the other side. And then we solve for dx in terms of du. So we get du over 2. Now we substitute for each part of the original integral that we have something to substitute for. Cosine is going to stay cosine. U replaces 2x plus 5, and dx is replaced by du over 2. Now the 1 over 2 becomes a constant factor, which can come out to the front. So we get the cosine of u du. Now remember that the cosine came after the derivative was done. So you're looking for the antiderivative. You're looking for something that when you take the derivative of it, you get cosine. So that would be someone.
Sine.
Fine, thank you. Got 2 volunteers that time. So this is going to give me 1/2 the sine of u plus a constant. Now the original integral had the differential dx, so we want to return to x. And so this is going to give us 1/2 the sine. Then we open the argument, 2x plus 5 plus c. Okay. All right, let's take a look now at the next one. We want to be looking at, whoa, I've got lots of space here. I don't need all this space. Okay, we'll take some of this space out. All right, looking at example 6 now. Example 6 is slightly more advanced because of the exponential. So you've got the integral of x e to the x squared. So you've got a power on a power. So I'll write this a little larger because sometimes it's hard to see what's happening. So this is what you have. Take a moment to look at that and see what you think the inside function is. What's the function inside the function? Let's hear from Roz, Lindsay, or Brittany. What is u?
X squared.
U is x squared. So that gives us du dx is equal to 2x. Abuse the notation and swing the dx around. And then divide by 2x to solve for dx. So you would get du divided by 2x. Now we integrate. We don't have anything to substitute for x, so x stays as is. Then we have e, which is a constant. X squared is replaced by u, and dx is replaced by du divided by 2x. That means that the x's will cancel, and we'll be left with the 1/2. The 1/2 can be brought outside of the integral because it's a constant. And we have the integral of e to the u du, which just becomes e to the u. Then we return back to the original expression for u so we can get back to x, which would be 1/2 e to the x squared plus c. Okay, let's bump up the difficulty level just a little bit. Let's take a look now at example 7, which has a more complicated looking integrand. So we have a fraction first off, and we have the square root of x plus 1 raised to the 4th power, and we have division by 2 square root of x. Now we have a couple of choices for u. So to recognize and identify, we're going to go ahead and list possible choices for u, or what would be the most obvious choices. One is the base being raised to the 4th power, so that would be the square root of x plus 1. One of them would be the denominator, 2 square root of x, and the other would be the denominator written as a fraction in fraction form. All right. So when you're looking at the possibilities that you have here for u, you want to imagine the derivative of one of these and try to imagine that how it would be taken by one of the other ones. So when I'm looking at this, the first thing I notice is the derivative of the first part, the derivative of the square root of x would give me 1 over 2 the square root, which is this part right here, which means that if I choose the first one for u, then I've already got part of du in the integrand. The other reason why it's a good choice is it is the thing being raised to a power, and that tends to be more commonly used as u than the denominator. So in this case, I'm going to choose u to be the square root of x plus 1. When I take the derivative of that, I get 1 over 2 the square root of x. Of course, chain rule, you multiply by the derivative of x, which is 1. So you get 1 over 2 the square root of x. All right. Now we're going to abuse the notation and swing the dx to the other side. So this gives me 1 over 2 the square root of x dx. And I want to show you a different method this time of solving these rather than solving for dx. Solving for dx will work. It will always work. It never fails. But there is another way that you can do it, which is looking at this problem and sort of pulling it apart into pieces. So we have the square root of x plus 1 to the 4th power times 1 over 2 the square root of x dx. Do you see that this piece right here is exactly that piece right there? Since they're exactly equal, then you can go ahead and make a substitution for the whole thing at once and call that whole thing du. And then we replace the base to the power function with u. So we get u to the 4th du. Right? So there are different ways of approaching these.
I got lost right there.
You got lost? Let me go back over it again. So what I did was I took the derivative of both sides of u, which gave me 1 over 2 the square root of x, chain rule times the derivative of what's under the radical, which is just 1. And then I took the dx and I moved it to the other side. So I got du equals 1 over 2 square root of x dx. Now I took the original integral and I pulled it apart and I wrote it as the numerator times the fraction 1 over 2 the square root. So I just pulled the pieces apart. So if I had something like a over b, I wrote it as a times 1 over b instead.
Yeah.
All right.
Thanks.
And then I looked at this part right here and just noticed that this was exactly what I have written over here. So this part is du. So I can replace this entire expression with du. And then I replace the base here of the power function with u. So I get u to the 4th du. Okay. And then applying the power rule, you would get u to the 5th, 4 plus 1, divide by the new power, add the constant of integration that I'm very partial to, don't leave off my plus c, and then return it back to x. So we have the square root of x plus 1 to the 5th power divided by 5 plus c. So the key to these is really making sure that you pick the correct u. We have 2 more to try. In this section of the section. All right, so we're looking at this function right here. This function is actually called the arctangent function. So this is actually arctangent when we're looking at this. So this is hyperbolic, not arctangent, my bad, hyperbolic tangent, which isn't really a trig function at all. It's abbreviated with TANH and it's pronounced tanch. So when you say it, you say tanch, like ranch, but with a T at the beginning. All right. Now, the hyperbolic trig functions aren't really trig functions. They're not angle related and they're not sides of a triangle related exactly. They're related to exponentials. And so what you have here is you have this e to the x minus e to the minus x over e to the x plus e to the minus x. So this is the relationship of the hyperbolic sine to the hyperbolic cosine. They got the name trig functions because some of their identities follow the same pattern that the trig functions do. So hyperbolic sine or sinh is equal to e to the x minus e to the minus x divided by 2. And hyperbolic cosine or cosh is e to the x plus e to the minus x divided by 2. So that when you take sinh and divide by cosh, you get tanch. And this is why they have trig-like names, because they do follow some of the same patterns that we see in the trig identities. These are most often related to what are called catenary functions. So if you want to know what a catenary is, it's kind of an interesting word. When you're driving down the road and you look up to the side and you see the power lines that are hanging between poles, when you look at those poles like this, and you see the wire hanging between the poles, that's not actually parabolic. It is a catenary function, which is a hyperbolic trig function. So the weight of the wire makes it go down in a pattern, in a shape that follows this catenary function. It is not as narrow as a parabola would be. A parabola would come in closer with the arms closer to the sides, and the catenary is more rounded. All right. So these are called catenary functions. The weight of any kind of string or wire or tube or rope under its own weight suspended between 2 points like a clothesline, that's a catenary function. Okay, we want to take the integral of this catenary function. So what we're going to do is we're going to have to look at this and see if we can identify u. This is a more difficult one because there's no obvious choice. We don't have a base raised to a constant power. We do have exponentials raised to powers, but the problem is the power's not always the same. Sometimes it's x, sometimes it's negative x, and they're not being multiplied by the other stuff, multiplied or divided. They're being added or subtracted. When we're looking for u tends to be something that's multiplied or divided with the other things, not something that's added or subtracted. So that's a problem. So really, there are only 2 possible choices for u. Because it needs to be something multiplied or divided with something else, it's either got to be the numerator or the denominator. Those are our only 2 choices. In that respect, when given the choice between numerator and denominator, it's almost always the denominator. Denominator trumps numerator. And the reason is what we're trying to build up is something that looks like 1 over u du. All right. So what we're going to look at here is we're going to look at letting u be the denominator expression, e to the x plus e to the minus x, the numerator of cosh. Now we take the derivative of both sides of that equation with respect to x. So we get e to the x minus e to the minus x. Now that should make you feel a little bit better, like maybe you've made the right choice, because you can see that this expression is in fact the numerator. So you do have the derivative as part of the integrand. It's in the numerator. Abuse the notation and swing the dx around. So we have du is equal to e to the x minus e to the minus x dx. And again, notice in this particular expression that what is here is also right here in the original. So we can instead simply substitute for du instead of having to solve for dx. You can solve for dx. It will still work exactly the same. It will be just give you exactly the same result. So now we're going to substitute. So we have the integral and the numerator, this e to the x minus e to the minus x dx, the numerator plus the differential gets replaced with du. And the denominator gets replaced with u, so that I'm left with the integral of du over u. Now the integral of du over u is one that you should memorize. This is one you should recognize. Does anybody remember what this one is? Maybe someone I haven't heard from yet today. Does this ring any bells? What derivative gives you 1 over u?
Natural log.
Natural log. So this has to be natural log. So this is going to give me the natural log of the absolute value of u plus a constant. Now remember that when we integrate 1 over u du, we have to put absolute values around the argument to natural log because it has to be strictly positive. So we've got to force it to be strictly positive. Now, because we started with the differential dx, we want to return to x for the antiderivative function. So we rewrite this in terms of the original u, which is natural log of the absolute value of e to the x plus e to the minus x plus c. Now, I should mention that because the exponential function, both of these are strictly positive, adding them is also strictly positive. So in this particular problem, the absolute values aren't necessary because the functions are positive already. But it's not a bad idea just to leave them, just to remind yourself that when you do take the integral of 1 over u du, you need the natural log of the absolute value of u. But again, in this case, they could be replaced with round parentheses because those are strictly positive functions anyway. Let's look at one more example. We have the integral of cosine of t over sine squared of t. Now, we're looking, if we can, for a function within a function. If possible, we're looking for composition of functions. If we can't find that, then the denominator is probably our next best choice. Do I have a function that's inside another function here? Do I have a more obvious being relative, obvious, not always obvious, right?
I think we do, right? Sine squared is within, I guess, x squared, you could say.
Yes, exactly. So we could think of this as cosine of t divided by sine of t being squared. And so you're right, sine of t is inside of x squared. And so we can think of this as a composed function where sine of t is the inside function. So we want to let u be the inside function, sine of t. Then we take the derivative with respect to x. We get cosine of t, abuse the notation by swinging the dx, well, not dx. What should it be? Not dx. It should be dt.
dt.
Yeah. It should be dt. It should match the variable. All right. So then we swing the dt around, and I do have cosine of t dt, so I can substitute directly, or just to point out that it does work the same, you could also solve for dt, which would be du over cosine of t. So I'll do the first method this time. So that would give us cosine of t over u squared, and dt would be replaced by du over cosine of t. So the cosine of t's would disappear, and I would get the integral of du over u squared. Now, what's my next step in order to be able to integrate du over u squared?
Replace u.
I don't need to replace u. What do I need to do with this? This isn't in a form that I can directly integrate. It's not 1 over u du, so it's not natural log. What would it be? I'll give you a
Quotient.
hint. I want to use the power rule, but it's not written in a form where I can apply the power rule. So what do I need to do to it?
U to the minus half or minus squared.
U to the
Bring it
minus
up.
2. Yeah, good job, Trevor. So what we want to do is we want to bring the u to the negative 2 to the top by changing the sign on the power. So u squared in the denominator becomes u to the negative 2 in the numerator. I want to apply the power rule. So I'm going to add 1 to the negative 2 to get negative 1. And then divide by negative 1. Then I add the constant of integration. That constant of integration is crucially important. It's a part of the antiderivative function. It's telling you that you don't know what the constant is. It could be anything. Now, I would probably clean this up a little bit. I don't like the negative in the denominator, and I don't like the u to the negative 1. So I would probably put the u in the denominator and the negative 1 in the numerator. And then the last thing, of course, is to return to the original value of u in terms of the original function variable, which is t. So that gives us negative 1 over sine t plus a constant. Okay, so this is sort of the end of u-substitution in indefinite integrals. The next thing we want to take a look at is how to do a u-substitution in a definite integral where we have limits of integration.